This is Polarized Light Microscopy in Archaeology. And this is supposedly lecture 7 and is about the other in pottery. So this is things in pottery that can be seen in thin section which are not minerals and rocks. One of the most important of these is voids. Voids are distinct from pores in having held an inclusion, other than gas, prior to firing. So a pore and the porosity of pottery will form due to gas being included in the pottery, which is typically a bad thing. And so you will have little pores in the pottery. But sometimes there are things in the pottery which have been completely driven away during the firing process, and you have that thing left behind as a void left behind by the thing. One of these is a vegetable fiber. These tend to be thin and elongate with longitudinal striations. Chaff is another type. Chopped straw, dung, these are all plant fiber voids that we can find in the pottery. Here is actually an example of pottery. Not yet, but basically here you have two types of clay. You have a fat clay, which is very rich in clay minerals. You have another type of clay which has got a lot of aplastic inclusions in it. So typically you do not have clay and then sand or silt being added to it. You will quite often have different sources of clays being mixed together. But another thing you often have is some sort of plant fiber. This is actually camel poo, and this sort of additive is actually very good for making pottery. It adds to the plasticity of the pottery, and is a useful temper. Actual temper. So this brings up the whole idea of tempering, and I've mentioned before with regard to minerals that in some cases, because it appears to be angular, like the calcite I was showing you, angular calcite, it looks like it had been added, so it was tempering the pottery, a deliberate addition to change the nature of the pottery. And these are often called aplastic inclusions in that case. And they aid workability during the firing. I should fix that slide one day. During the working. And they reduce the shrinkage during drying and provide desirable properties during the firing. Oh, no, too fast. And also provide desirable properties to the finished vessel. So I usually use this slide because it shows these are all mineral inclusions, and this has few and this has many, because this is a handle which has been added to this piece of pottery after this piece of pottery has already dried. And so that means the shrinkage will be much less, and it's less likely to fall off. Whereas if the pottery vessel and the handle were made at about the same time, then they would shrink at the same rate and it wouldn't be a problem. But in this case, they allowed it to dry, and here they're making sure it doesn't shrink too much. So plant fiber is very useful for, makes it very useful during working. I often make it more plastic. It's useful for reducing the shrinkage. During the firing, it probably doesn't greatly contribute to the firing, but it can provide desirable properties to the finished vessel iron. It has been suggested it creates porosity, which I believe is incorrect, but it does, for instance, if there's a lot of voids from plant fiber, it does make the vessel lighter. But it's mostly that the advantage of plant fiber is that it's very easy to add a lot of plant fiber. It doesn't create a lot of problems, and when it's fired it goes away, so it's not going to at least provide undesirable properties to the finished vessel. So here's a thin section with some plant fibers. Here you can see this is still got relics. If this is a completely reducing conditions firing here, the fiber is entire black, as you can see. And so when that happens, sometimes the carbon isn't driven away. Typically for an oxidized firing, the carbon and the oxygen will go together and come out and create global warming. But in this case, it's still in the pottery. And so you can clearly see that this is a plant fiber. It looks like a nice big bit, and it seems to have finite ends. It's possible that this is something like chopped straw or something. Here's another bit. Most of these inclusions look like they were probably plant fibers, and these voids, shall we say. And here's another one. You can see here it's slightly curved, and here again it looks like it's slightly curved, and possibly here. So it's possible that this is chaff. Chaff is the outside shell of things like wheat, of which there is a lot in early agricultural civilizations, and so it makes a very useful tempering agent, but it's nowhere near as common as many archaeologists say it is. And they often say, look at any plant void, any irregular void that looks like it might be from a plant, and say, oh, this is chaff tempered, when in fact when you look at things in thin section you can see all sorts of other types of plant fiber other than chaff, or certainly things which are not chaff, which are plant fiber. So there. Here we have very long stringy ones. So this looks like it might be grass or something. It's hard to tell. And here, look at this one. It's sort of like ribbony. This has lots of ribbony inclusions in it. So, and it might be useful at some stage for someone to actually write a doctoral thesis on plant fiber voids, of which we get a lot in the prehistory of the Middle East. But all we can really do at the moment is say, well, this is clearly some sort of plant fiber void, and see that it is distinct from another one, because it doesn't look the same. But what would be really cool is if somebody actually went and tempered lots of pottery with lots of different plant fibers and see what they look like in thin section, experimental archaeology basically, and see what sort of plant fibers create different things. And this is a bit of plant fiber here. This is interesting. This is a phytolith. So that's a siliceous framework within certain grassy plants, and this is very common indeed in the Nile, and it's probably papyrus. You do get these phytoliths in other parts of the world, like in southern Iraq, where there's a lot of reeds, but you get a lot of it in the Nile. So it's again very distinctive, but it mostly tells you that this comes from a river somewhere. So calcium carbonate, calcite, can also be destroyed in the firing above 750 degrees centigrade, and you may see voids like curvilinear shell, rhomb-shaped sparry calcite, irregular micritic inclusions, or rounded micritic limestone, or oolites. And so what I'm going to show you here is, you can imagine if this was fired to very high temperatures so that this disappeared, it would be left with very distinctive rhomb-shaped voids in the pottery. The sparry calcite, micrite, same slide. And also you may have fossils, which also can fire out. This is actually a clay nodule, which we shall get to later on. Oh, in fact, we'll get to it right now. Argillaceous inclusions, which is always difficult to pronounce. Argillaceous inclusions. So they are inclusions which have argillus in it, which is clay. So it's a clay-rich inclusion, which is actually a lot more complicated, it sounds like. So there are a number of different types of argillaceous things we get in pottery. One, of course, is shale, rock, which we talked about before, like last time, with pottery. So a shale inclusion, I'll show you all of them first, and grog, and clay nodules. And so the distinctions between them is that shale is a lump of rock. It has a very distinct boundary, and it will have the shaly structure, it'll have that facility that I showed you. Remember the distinction between a shale and a mudstone. So a shale will be fissile, a mudstone will not be. Shales are far more common, so it's far more important. Grog is a term used by archaeologists to refer to crushed pottery. So someone has taken pottery and ground it down to add to the pottery, which works very well as a temper because it's just more pottery. So you can add as much of it as you like. And if the clay is really problematic, just keep crushing up more old pottery and adding to it. Just as long as you have enough to stick it all together again. This will have distinct boundaries. The internal structure will be pottery-like, so it'll look like the rest of the pottery, only be different. And another thing you'll get will be clay nodules. So you have, well, the thing I just showed you actually probably had a clay nodule in it. It wasn't any other type of argillaceous inclusion. And this is what you'll get when you're mixing clays together. If you remember that slide a couple of slides back of two different basically piles of clay being put together to make a workable paste, you can imagine that if that's not mixed very well, and like milling clays to make a very fine-grained material is not common in the ancient world, and so they it will have lumps of the different raw materials which have been processed. But I don't forget we're looking at this microscopically, so it's very difficult to get microscopic lumps out of your pottery paste. So the clay nodules will have very indistinct boundaries because they just sort of smoosh into the surrounding material, and will have no internal structure because it's just a lump of clay. So the question is, what is this? What do you think it is? I mean, it looks like it has a distinct boundary, but the structure of it looks kind of like more pottery. And it's very distinct from this pottery. This has got a lot more iron in it probably, but you can see they both have a pottery-like structure of random inclusions. So that's probably grog. Here we have something you should know by now, the Godin Tepe Shaly petrofabric in plain polarized light here. And so here you can see the argillaceous inclusions, and here this one looks a bit more argillaceous and a bit more distinct, but it has that very fissile structure. You see this one has a very fissile structure, and so this orientation shows you that this is shale. You would not get pottery that looked anything like this. This one looks a bit more like pottery, but it is also shale with a lot of silt in it, it looks like. So that's shale. Here's another thing, and sometimes you'll find these things are not as obvious as you think. Typically, if it's something that's been added, like grog, it's been crushed to about the same size, more or less, and added, and so there's a distinct amount of it. If you find one teeny bit, or even one quite big bit, it probably isn't grog, because they're not going to get like a bit and throw it in. Now this has something that you might think looks a bit like grog, especially on this side. The boundary's quite distinct. But you see on this side, it really sort of smooshes into the matrix. And another thing is, if you like sit back and look at the whole thing at the same time, you'll notice that certain areas have a lot more inclusions than other areas. And you see there's even a slight color difference between this area over here and this area in the middle and this area over here. And so it really looks like certainly the inclusion. Sometimes the color is due to the firing atmosphere, but in this case, it really looks like this is being badly mixed together of different clay raw materials. Here you can have a lot more silt in here, and this seems to have a lot more of the clay. And this looks like it represents the original clay-rich component, both of these things. So they look like clay nodules. Here you can see another, it completely fuses into the surrounding matrix. And here. This is grog. You can see here it's sort of come apart from the surrounding matrix. This is from a site in western Iran called Sangalan Tepe, where there's a whole bunch of these, which is particularly interesting in that, see, here is another grog, and inside this grog is another grog. You know, so they must have ground the pottery to make this pot, and then broken that pot. When that pot was broke, they ground that to add to this pottery. In one occasion, is the next one like that too? Yeah, this one's even bigger. Look. So here's a big piece of grog with a piece of grog in it. And looking at the mineralogy of these at Sangalan Tepe, I assume this is still Sangalan Tepe, there was one in which the petrology of the grog was incompatible with production at the same place that the pottery within the bigger piece of grog was. So this must have been made, or most likely was made, at a different place from this. And the pottery was so different from this that it must have also been made in a different place. Which would suggest that this pottery was made in one place, taken to another place, and that pottery was taken to a third place. So this would suggest that this population was very, very mobile and moved around a lot, possibly transhumant. And so they were moving around a lot, and one of the things about grog is it's always predictable. So if you're going and making pottery somewhere where you don't often make pottery, you're more likely to be successful in adding more grog than finding something else to add to the pottery as a temper. And so for this mobile population, they probably really liked grog. And apart from deliberately added things, occasionally you get stray things in it. And it's important not to worry too much about stray things. But this is a stray thing that I found in a piece of pottery from Bahrain, which is a piece of bone. You can see it has the structure of bone. So that's a piece of bone. So this is a nice shiny piece of pottery. This is made in the later 15th century in Turkey, and it has certainly the attributes that we'll be talking about next, which is different ceramic bodies, glazes, and paints. So this involves the use of a scanning electron microscope. So we'll be looking at some images generated by that. And in that you put the sample inside the device. There it is. And one thing you can do is bombard it with electrons, which scatter back to create images. And the images that are created by how much backscattering there is. So the higher the atomic number of the elements within the material, then the lighter the image is of it. For instance, this is tin oxide, in fact. And so this has a high atomic number, and so it's white. This is probably a piece of quartz, and so it has a much lower atomic number, and so it's grey. This is a hole, and here the pottery body is sort of like various sort of atomic numbers, like clay in here and in inclusions and things like that. So that's how you make one of these backscattered electron images. And so, you know, here you can see the atomic number is so an iron, a lead rather, or here is tin. So here's tin. Now that would have been better to point show you, wouldn't it? Tin. So tin is quite high, and higher than all of other things like silica. Here's silica, which is what the quartz was made of mostly. So another thing you can do is have a focused beam of electrons, which will zap microscopic bits in here, like specific inclusions or areas of, say, glaze, and create this spectrum, which shows you effectively what elements are in it. It's tremendous fun. So this is using X-rays. So you have radio waves, microwaves, infrared waves. That's what you get heat things from. You know, the visible light, which is what we use in our microscopes. Ultraviolet, which was a very horrible movie, which I would recommend you never ever watch. And X-rays. So X-rays are here, and you have gamma rays, which turned the Hulk into Hulk, and you have cosmic rays. This is the most appropriate image I would find for a cosmic ray. So so X-rays are here along the electromagnetic spectrum, and they are generated by, and we're back here again, what happens is these electrons go banging into the electrons, and they will knock one out, and what happens is another one will fall into its place, and that will give off a distinctive X-ray, and that's what creates this. And so that, and sometimes there'll be a number of lines for which of the electron rings it fell in from. So that's how X-ray fluorescence works. So stone paste is one of the first things we'll talk about. So stone paste is the medieval version of a paste mostly made of quartz, and it started off, it seems, in Iraq in the 9th century, where they started adding glass to pottery. This is done in Baghdad. So that seems to be what's going on. I have no idea why they added glass to pottery. It sounds like it might be a good idea, maybe make the body more vitreous, but it doesn't seem a lot to have come out and gone into the body. But adding glass is an important aspect of this technology. So it's possible that, here's Baghdad, it was known possibly by the potters of Basra, because the potters of Basra then went to Fustat, or Old Cairo, and the Basra potters made lusterwares, very important type of pottery in the 9th and 10th century, and then they went to Fustat and started making it there after about 975. Now, the luster pottery is very demanding. Here's one, and it needs a very typical type of tin opacified glaze to work with because it's just very difficult. And so another thing that is difficult is having a glaze that fits with a ceramic body, and quite often if they don't fit, the glaze will just come right off of the ceramic body. And so they needed to make a body that worked really well with their glaze, because otherwise they couldn't make the lusterwares. Yeah, I'm going to get around to explaining it. So the way you make lusterwares is we have a couple of treatises which tell you the sort of thing in it. The consistent things is you have silver and copper, and you create this paint with all this other stuff in it, like iron sulfides and arsenic and oxides and other stuff, vinegar, sulfur, and apply this paint. So it's this thick paint, but what happens is that it's fired to a low firing temperature. It's not a high fired process. You make the vessel, you glaze the vessel, and then you apply the paint and heat it up so that the silver and the copper come out of the paint and fuse to the surface. So if the temperature is too high, all of this paint will fuse to the surface, because you need the glaze to get sufficiently molten that the silver and the copper fuse to it. If it's too high, then this will fuse to that. If it's too low, nothing will happen. If any oxygen gets into the kiln, the silver and the copper will leave. So it's very important that this glaze, they carried on having this glaze. Oh yeah, and then you wipe that off afterwards if you fired it properly. And so what I think that happened is they started playing with the fabrics. And so this is the earliest of what looks like the beginnings of stone paste. And so here, this thing here is actually an inclusion of glass. And what happens when you add glass to this matrix is that crystals grow within it. Wollastonite and enstatite and things like this. And also in here is quartz. This dark thing is quartz. Some of these are actual voids. And the rest of this is clay. So you have clay, and you have quartz, and you have glass. And there are no other inclusions in it. So this is not a typical Egyptian clay available in the Fustat area, because they all have inclusions in them. People have been doing lots of petrographic analysis in this part of the world, and you don't get a lot of clay with nothing in it. And so it looks like they have deliberately levigated all the stuff out of the clay to add quartz to it and glass to it, quite a lot of glass, to make the ceramic body. And this was quite rare because they were making a sufficiently workable body by modifying Nile alluvium with calcareous clays. But once they worked out how to do this really well, it became the predominant type of ceramic, which is real stone paste. And so this is 8 parts of quartz, 1 part of clay, and 1 part of glass. And so the clay keeps everything together during the forming process, and the glass will fuse everything together in the firing to make this white, consistently performing body. Oh, clay, yes. So this, of course, we can do petrographic analysis of. In fact, you may have even seen a stone paste, and you're looking for things like this in it, but also looking at the nature of the quartz. Now, there were these siliceous pastes. The British Museum calls them glazed composition, which is, a name. A lot of people call them faience, which is also a name, but it's not a very good name because it basically says it's from Faenza, which it isn't, and that sort of attribution is always a bit dodgy. Sometimes people call these things fritwares, or frit, which is also completely erroneous because it is not frit, and it doesn't include frit added to it. It includes glass and quartz. Frit is a process on the way to making a glass in certain circumstances where you fuse the glass materials, which things like alkalis and glass, fuse them together without it becoming molten. And that is in no way related to this, although superficially it may be thought to resemble it. So fritware is just completely technologically erroneous. So, I'd rather you call it faience, at least it's just a silly name. So there are a number of ways this is made. This is actually at the ROM, it's very nice. One is through efflorescence. And in this, so this is difficult to make. All of these ancient glaze composition techniques lack clay. It's one of the biggest distinctions between the ancient techniques and the medieval technique is the medieval stone paste has clay in it. And the clay keeps it together during the forming. But what was keeping the ancient material together is hard today. They might have had like some sort of gum or something to keep it together, but it's hard to exactly see how it worked. Typically, certainly looking at the objects, they look like they were molded, so it would be impossible to throw these things, and so they're just molded. They stay together long enough for the firing, and in the firing they fuse together sufficiently to stay together. In some cases, glass had been added to the quartz, but quite often it's actually just the glaze material on the outside which fuse everything together. In efflorescence, it is the glaze mostly which fuses everything together, and so in this there are salts added. I think sodium and things like this are a flux which enables silica to melt at a lower temperature, and so is what you could make a glaze with. And so they are allowed to dry, and the salts effloresce to the surface, and so they form a layer around the surface, and they will then form a layer of glass when it's fired. You can also apply a glaze. So a glaze is a vitreous layer on the outside of ceramic, which this is an amusing graphic here, which is like this thing with a bit of glaze on the outside. So it's not a layer. It'd have to be a very small thing. And you take a vessel, say this is a teeny tiny pot, and you dunk it in a solution, probably water, with suspended within it very finely ground glass, and this glass will then stick to the outside and fuse to it during the firing. And there is cementation, and this is when you have the object. This tends to be things like beads, so this is I always say a round bead, and it's actually embedded in the glaze materials. And so what happens during the firing, the glaze materials come out and fuse to the quartz, and then you can break open all this sintered material, and what's left behind is a bead. So it actually works quite well, and there are big production centers for beads and things like that. But to make vessels, you would need one of the other techniques, probably. So another thing you will see in thin sections are slips. So here you can see this is a ceramic body, but this is the slip, and this is using the term slip very vaguely. And here on the outside of that is the glaze. And we'll get back to why that looks different in a minute. So slip, sensu strictu, shall we say, is actually clay in suspension. So this has been levigated and is no longer got anything in it other than clay. And so that is what a slip is. And so this is very easy to make liquid. Add water to it, it becomes very goopy. And you can apply this to the outside of a vessel. Like this is being poured all over the vessel, and you could dunk it in it or paint it on it, and that's slip. So that's a true slip made of clay. This is how ancient pottery is painted. It's not just a paint. It tends to actually include, not always, but typically it will include clay. And so it's in this case, probably this is maybe manganese or iron added to clay, and then that is painted to the surface and then fired. Sometimes people use the term engobe, which is French for slip. It's like gobbed onto the outside, onto it rather. But this actually works quite well sometimes when the covering is not clay. And this is actually a stone paste slip, one might say. It's probably not true stone paste, but it is actually made up of crushed quartz, which may actually be one of the ideas behind the whole idea of stone paste, because this was made in Iraq, in Baghdad, before stone paste was developed. So in Basra and Baghdad, they were making a white slip for their pottery by using crushed quartz. Quite clever, really. So you might have things like that. Then there are things like a false slip, sometimes called a wet hand finish, because that's how you obtain it. So a false slip is a technique you can use to bring clays to the surface. Sometimes burnishing will also help with this, because burnishing pushes in things like inclusions and orients all the clay on the surface so that it's horizontally, so it looks very, very flat, like it's had a clay-rich slip applied to it. A false slip like this, you see the wet hand on the outside. If you just like keep using that wet hand on the surface, it also brings the clays out of the paste, and it brings out the orientation of the clay minerals parallel to the surface. And so what that looks like in thin section is a bit like a clay, but the boundary between the slip and the body is not very distinct. And you can have a self-slip, which is from efflorescence, a surface recrystallization. And so here you will get crystals growing on the surface. Tends to be in pottery with possibly salt in the clay. And this is an interesting thing. This is an SEM picture. This is the clay body on this side, and this is glaze. And these are crystals of wollastonite, which is a calcium silicate. So it's possible that this distinct, the grey ones here, that this and this creates a white slip on this pottery. It looks like, because this is a red firing pottery which is white on the surface because of the wollastonite crystals, which probably started off as being some sort of self-slip thing going on. And so glazes, which I talked a bit about here. So here is the glaze on the outside. This is a lead fluxed glaze. And so here we have all the, cations and anions going together, linking together, and things like silicate in the silica, rather, SiO. And the Si and the O get together, and they can make a solid. And they can make a liquid, and they can make a gas. Usually depends on the temperature and things like that. But you have something over here which you know quite a lot about now, which of course is crystals. Crystals are more solid than solids. They are in a crystalline state. And you have something down here. You have a supercooled liquid, and that's what glass is, including volcanic glass. The structure of it is like completely random. And this is an example of someone trying to capture an image of it. This is a crystalline structure, and this is a glass structure. And you can see that's sort of like, you can see the silica tetrahedra like a conga line going through the quartz, because you're just moving around, and boom, it's frozen like that. So it's like, you're in a conga line and somebody blows the whistle and you have to stop. And that's what glass is. See, this is interpretation of the elements in the glass. So glazes are an anthropogenic glass, predominantly made up of silica. So the melting temperature of silica is high, 1610 to 1713 degrees centigrade. The kilns we're dealing with will not go that high. That will completely not only melt silica, it'll melt all the pottery into a molten lump. So you want something to make silica melt at a lower temperature. Oh yeah, there's the firing temperatures. Some kilns can go higher than that, like 1200 degrees centigrade for porcelain, but the Middle Eastern kilns are very unlikely to get that high. So you require a flux to enable the quartz, the silica, to melt at a lower temperature. So the fluxes we get in the Middle East, lead is very important. So the glaze will contain 50 to 60% of lead, like galena, lead sulfide. Appeared in the 1st century BC, and it's very widespread technology. I don't think anyone really knows who started it, because it occurs in the 1st century BC from China to the Mediterranean, and someone must have come up with it, or one assumes. Here, for instance, is a nice Chinese one from China, and here's a nice Roman one from the East Mediterranean. So another important group are the alkali fluxes, containing up to 20 to 30% alkali elements such as soda and potash, and will include plant ash sources. So these are halophytic plants that like salt, grow in the Middle East a lot, but you can make it out of other, say, coastal plants. And you can also make it out of the mineral natron, although it tends to just be in Egypt. There's a lot of natron there. Originally developed in Mesopotamia, on the 3rd millennium BC, it was actually on faience, or composition. After about 1500 BC, it was on clay. So here we have an alkali glaze on Parthian pottery from Iraq. Yes, a later one, Sasanian. And here are earlier, so these are our faience beads, or glaze composition beads, with an alkali glaze on the outside, actually keeping all the quartz together. So this is a Seleucid glaze. So from the time of the Seleucids, the successors of Alexander, so that would be like 1st century, 2nd century BC or so. And here it's quite interesting. So this is the clay on this side, and this is the outside over here somewhere. And it has these crystals growing in it. And what these crystals, will be in here, would be wollastonite and augite and things like that. And diopside, one of those pyroxenes. And so these crystals will actually render a certain amount of opacity to the glaze. But what they seem to have developed in the early Islamic period in Basra was they first started applying tin. At first it seems to just be on the surface. And so the dating evidence for this is that they would have started in the 8th century. We have pottery from excavations which put it in that date in Susa and other sites in Iraq. And we also have this sequence which explains the development, where the early pottery with tin in the glaze would have had a little amount of tin in it, and it just stayed on the surface. And so here you have the white, here is tin, and in this glaze you have the same things you had in the pre-Islamic glazes. You'll have lumps of quartz, undissolved quartz, you'll have crystals of enstatite or wollastonite and things like that. And this is the beginnings of what we later call tin opacified or tin glazes. There's the body, there's the glaze, there's some quartz, and there's the tin. That's a hole, a void. Although actually that's not a void because that's a gas bubble. So it's a pore. Later on, this is like the next phase. We still have these silicates growing in the fabric and also quartz. But there's more tin, and so now the tin is disseminated throughout the pottery. But in the second phase of production, they're still reliant on pre-Islamic technology to make the glaze really opaque. And so it would have taken quite a long time for them to develop a truly tin opacified glaze. This is actually a Fatimid one, although it did develop originally at Basra. and would have developed in Basra by about 800 AD. This is one of those balastanite slip things I was telling you about. So here is the glaze, and as you can see, this, I don't think you can quite see, but it's got a red clay and a white slip on it, but this is not a slip, it's balastanite crystals. So this is probably a false slip of sorts. And I think these are supposed to be made in Beirut now. Someone's been doing some analysis of this type. So another thing we get is paint. So sometimes you get clay paint, in which case you'll have a lump of clay on the outside, like a layer of clay. But this is a different type of paint. This is called an underglaze paint because it's under the glaze, although you can have a clay-based paint under the glaze too, but this is called an underglaze paint in the literature. And this is just oxide. This is actually chromium oxides, and that's what makes paints like this. You also have cobalt blue and iron for the red. So again, this is actually a medieval paint in this case, but you do get other sorts of paints as well, chromium pigment, like I said. And so I think that's it for this lecture. Thank you.